Welcome to the first session of our webinar series on ceramic additive manufacturing. Today, together with Lithoz, we will discuss the global perspective and the outstanding capabilities of ceramic additive manufacturing, a technology that's rapidly gaining momentum around the world. Before we begin, please allow me to introduce myself and infoTRON. My name is Enver Efebaci. I am the Business Unit Manager for Ceramic and Metal Additive Manufacturing Technologies at infoTRON. My team and I would be pleased to be your first point of contact for all technologies related to ceramic and metal additive manufacturing at infoTRON. infoTRON was founded in 1994 with the aim of developing products and creating added value. For 32 years, we've been working to create value for our customers. Since the day we were founded, in addition to our system sales, as you can see on the screen, we have continued to provide services to our customers in many areas such as product design, 3D scanning, modeling, and reverse engineering, part printing services, and simulation projects. With its presence across all industries in Turkey, infoTRON continues to be one of the most important 3D technology companies in the country with its valuable references and ongoing projects. Today, we are a company of around 100 professionals dedicated to delivering advanced engineering solutions and innovative manufacturing technologies. At infoTRON, we have never seen additive manufacturing as just a manufacturing system. We see it as an integral part of the wider manufacturing ecosystem alongside other manufacturing methods. For this reason, we manage our technologies in several key areas: production systems, software solutions, powders, powder development, parameter development, and post-processing. Within this perspective, our goal is to be a company that provides solutions across all stages of additive manufacturing while collaborating with strong and leading technology manufacturers. With this vision, we collaborate with leading manufacturers across a range of technologies, including software, automation, EBM, DED, aerosol jet, LPBF, HIP, electroforming, and many more. Today, we are joined by Gerardo Igler, Business Development Manager at Lithoz, and Thomas Prochaska, Head of Materials R&D at Lithoz. I would like to thank them in advance for this session, which we have prepared with a focus on technology and materials to help you become more familiar with ceramic additive manufacturing technologies. Dear participants, please feel free to share your questions with us throughout the webinar. We will be happy to answer them at the end of the webinar. With this brief introduction, I would like to hand over the floor to Gerardo. Gerardo, the word is yours.
Welcome to our webinar and thank you for joining. My name is Gerardo Igler. I'm Business Developer at Lithoz, and I will give you a short introduction to Lithoz and to ceramic 3D printing. This is our team, and together we focus fully on advancing high-precision ceramics additive manufacturing. Let's begin. Let me give you a quick overview of Lithoz as a company. We offer a complete solution for ceramic 3D printing: the printers, the materials, the software, and also customized developments. Quality is a key part of our work. We are certified to ISO 9001 and also to ISO 13485, which is the quality standard for medical devices. Lithoz now has more than 100 employees and 4 locations worldwide, 2 in Austria, plus offices in the USA and in China. There are over 200 Lithoz machines installed globally, and around 25% of customers operate 2 or more systems. This shows that once companies adopt our technology, they usually continue growing with it. Here you can see a selection of our customers and partners from around the world. Lithoz works with companies and institutions across many industries, from aerospace and defense to electronics, medical technology, research institutes, and universities. This includes well-known groups as Safran, Bosch, Rafael, Steinbach, Baikar, and TEI. as well as leading research institutes like Fraunhofer, IKTS, KIT, KIT, and many universities worldwide. The main point of this slide is to show that LCM, lithography-based ceramic manufacturing, is already used in demanding applications and by organizations that require high reliability and high performance. It also shows that the technology is not experimental anymore. It is already part of real industrial workflows. Now let's look at a very important question. Why ceramics? This will help us understand why ceramic 3D printing is so powerful and where it brings real value. Most of you are already familiar with polymers and metals in additive manufacturing. These materials are excellent for lightweight structures, complex shapes, and fast development cycles. But there are environments where even the best polymers and metals reach their limits. For example, extremely high temperatures, aggressive chemicals, or demanding electronic applications. In this part, I will briefly explain why ceramics are interesting for additive manufacturing, what makes them more challenging to process, and how Lithoz addresses these challenges with industrial technology. After my section, my colleague from materials engineering will go deeper into the different ceramic material families and their applications. To begin, here are a few examples of environments where conventional additive manufacturing materials are simply not enough. This slide shows why ceramics are so valuable in high-performance applications. Ceramics offer properties that metals and polymers cannot achieve. They provide excellent electrical insulation, strong resistance against chemical corrosion, and very high mechanical stability. Materials like zirconia offer outstanding bending strength, and others provide transparency or very high thermal conductivity, such as aluminum nitride. Ceramics also handle high temperatures, thermal shock, wear, abrasion extremely well. These are the reasons why many industries rely on ceramics when other materials fail. In medical and dental applications, ceramics offer a different set of advantages. They are biocompatible, and some materials are even bioresorbable. Others, like silicon nitride, support osseointegration and have anti-infective properties. Ceramics also provide excellent electrical insulation, translucency in the case of alumina, and a very clean surface quality, which is important for implants and instruments. These properties make ceramics a strong choice in areas where safety, cleanliness, and long-term stability are essential. This is why ceramics play an important role in many modern medical and dental devices. This quote from our Chief Technical Officer captures it very well. Many of today's biggest challenges will need high-performance materials, and often a 3D printed ceramic part can be part of the solution. That's why this technology is becoming more and more important. Now that we have seen where ceramics are needed, let's look at why they are so important, specifically in additive manufacturing. Ceramics in additive manufacturing are not here to replace metals or polymers. They are a complementary material class that fills the gaps when other materials reach their limits. Ceramics are engineered for extreme conditions, high temperatures, strong wear, aggressive chemicals, and demanding electronics environments. On the right, you see a comparison of typical properties. Polymers and metals perform well in their own areas, but ceramics stand out when it comes to temperature resistance, electrical insulation, chemical stability, and wear resistance. These are exactly the properties many additive manufacturing users need today. And this is where ceramic additive manufacturing brings real value. Now, independent of the exact ceramic material, the design advantages of additive manufacturing are similar to what you already know from metals and polymers, but in a much harsher environment. Conventional ceramic manufacturing is great for simple shapes that can be pressed or machined, but internal channels, complex 3D flow paths, porous structures with defined geometry, or very fine details are extremely difficult or expensive to realize. With ceramic additive manufacturing, especially lithography-based ceramic manufacturing, we can integrate these features directly into the part. Internal cooling or fluid channels, lattice structures, and miniaturized features. In many cases, we can combine several functions, for example, fluid handling, thermal management, and electrical insulation in one single component, reducing assemblies and interfaces. Later in the materials and applications talks, you'll see concrete examples, filters, reactors, medical devices, and more that benefit from this combination of design freedom and ceramic performance. This example shows how ceramic additive manufacturing can combine several functional features into a single tool. This part you see here is an arthroscopic knee shaver, and it actually consists of two ceramic components that work together. What is important to notice is the scale. The reference here is only 10 millimeters. 10 millimeters is extremely small, about the width of your fingernail. So achieving this level of detail is very challenging with conventional manufacturing. As the features appear on the slide, you can see the different channels. Channels for rinsing, a channel for the light source, a channel for drainage, and the rotating cutting blades in the front section. All of these complex internal structures are created in one production step with no assembly work needed. This is a good example of how ceramic additive manufacturing can deliver compact, functional designs at very small scale. Next, I'd like to introduce an important topic in ceramic 3D printing, the thermal processing challenge, and why it plays such a critical role in achieving high-quality ceramic parts. Ceramics are attractive for many applications, but they are not as easy to process as metals or polymers. Metals can often be melted and re-solidified, and polymers can be melted or cured directly. Ceramics cannot simply be melted. They must first be shaped and then densified through sintering. In ceramic additive manufacturing, our first step is always the same. We print the so-called green body. This green body is made from ceramic powder mixed with an organic binder. At this stage, it has the right shape, but it is not yet a ceramic part. Everything that follows depends on how well this green body is printed. Here is why the green body step is so critical. Since ceramics cannot be melted, we must work with a slurry made of powder and binder. This slurry is printed, and then we have the green body, which is still soft and full of binder. Only later, during the binding and sintering, we do achieve the final ceramic. If the green body is not printed correctly, for example, if the print is not uniform or the features are not clean, it becomes very difficult to reach high density and low defect rates after sintering. So the entire success of ceramic additive manufacturing starts with getting the first step right. Once we have printed the green body, the real work begins. In the green state, the part is made of two components. The yellow dots represent the ceramic particles, and the gray areas represent the organic binder that holds everything together. At this stage, the part is still fragile and not yet a ceramic. During thermal post-processing, we first remove the binder, and then we sinter the ceramic particles together. As the temperature increases, the ceramic particles bond and the structure becomes dense. This is what transforms the printed shape into a true high-performance ceramic part. The second image shows the result we aim for, a fully dense microstructure with no pores and no defects. Achieving this density is essential because it gives the final component its strength, reliability, and high-performance material properties. Now let's look at what makes our lithography-based ceramic manufacturing unique and why this technology achieves such high precision and quality. When we talk about lithography-based ceramic manufacturing, the main point is density. Ceramic parts only work if they are fully dense. Even tiny defects can make them fail. Lithography-based ceramic manufacturing achieves this because we work with liquid, photocurable ceramic suspension. This allows the ceramic powder to be shaped with very high precision before it is sintered. A major advantage of LCM is material flexibility. We are not powder manufacturers, which means we can turn any commercially available ceramic powder into a printable slurry. This gives customers full freedom to choose the ceramic that fits their application. With the DLP digital light processing exposer, we can create ultra-fine details and very smooth surfaces, and the final sintered parts reach true industrial performance. This combination of precision, density, and material freedom is what makes LCM outstanding. This slide is a short transition to the next part of the webinar. One of the strengths of ceramic additive manufacturing is that we can use the same additive manufacturing process for many different ceramic material families. The design freedom stays the same, but each ceramic class brings its own performance profile. For example, high temperature resistance, electrical insulation, chemical stability, or biocompatibility. My colleague will explain these material families in more detail and show where each one is used. These slides bring the main message of my part together. Ceramic additive manufacturing lets us use additive manufacturing in environments where metals and polymer no longer work. High temperatures, strong wear, chemical exposure, or demanding medical devices like the one shown here. With LCM, we keep the same design freedom you know from other additive manufacturing technologies, but combine it with true ceramic performance. This brings us to the next part of today's webinar. Thank you for your attention so far. I'm now happy to hand over to my colleague, Thomas Prochaska, who will take you into the different ceramic materials and their applications.
So now, as Gerardo mentioned, I will go into the details about our materials a bit. So our technology, one of our main advantages is that our technology is incredibly versatile. So we can manufacture nearly all ceramic to a 3D printed green body. Some of them are more challenging than others, but in the end, we manage. So as you can see, the range from the ceramic material, our ceramic material portfolio is pretty large. So we can process silicon nitride, aluminum nitride, then a classic aluminum oxide and zirconium oxide, and of course, the mixture of both being represented in toughened alumina and toughened zirconia. We can process corrugate, and of course our medical materials, the calcium phosphate with the 3-calcium phosphate and the hydroxyapatite. Then we have the group of the silica-based casting cores and lithium disilicate for the silicates, and curiosity like the moon dust. And today I will unfortunately not have time to go into detail for each and every material. Today we will focus on these 6 materials. So let's start right away. So the first one I want to show you is aluminum oxide. Aluminum oxide still is one of the most sold and used ceramic in the market. It has many applications, and as in the traditional ceramic, it is the easiest to manufacture. On the right-hand side, you can see the microstructure that we achieve in our technology and a very nice demo part that shows an application for a nozzle, where is an application where ceramics most shine. Alumina in itself has a very broad range of applications, be it technical, medical, or electrical. As a thread guide, for example, or as medical devices for permanent implants or devices. You can even make dental brackets with a translucency or use it as a housing device for medical applications. An example that you saw before on Gerardo's slide is the Da Vinci arm. So I want to show this part in a little bit more detail because I personally find it really impressive. In this case, the machine was developed and they need to fill and they had an existing problem. They needed a light channel, and they needed it to be on a material that can stand the high demands for the applications. So they 3D manufactured it, and the tolerances were relatively small, and so were the geometry overall. So you can see the tip of a pen on the right hand side, and this of course was very challenging, and with the precise angles that we needed to achieve. It's a very good representation of where LCM really shines. It's the high precision and the high demanding applications. Another of our application for aluminum oxide, which is a very high end, is the dental bracket. So for the dental bracket, the translucency is very important. Which if you think ceramic, translucency is not the first thing you think of, but the finish is very, very nice, and the ceramic properties that you can achieve by this are outstanding. The aesthetics are beautiful, and we have advantages like that you can realize designs which you could not with injection molding. For example, you can print sharp angles in 90 degrees that you could not demold traditionally, and you are now able to manufacture via LCM. Here is another close-up of what you can achieve with our technology. I personally, this is one of my favorite pictures that exists from aluminum oxide, since it really shows you can hide nothing on this resolution, and it really shows the translucency that we can achieve. The next one that I would like to present is zirconium dioxide, often called zirconia. Zirconium dioxide is yttrium oxide stabilized, and it has an excellent mechanical strength while maintaining a high fracture toughness. It's sometimes referred as ceramic steel, and it has a lot of good properties. Like it's very hard, like most ceramics, but also the surface finish of zirconia is special since it has a certain shine to it and is often very smooth. It's an electrical insulator and also a thermal insulator. It has a high dielectric constant, and it's bio-inert and food compatible. On the left-hand side, you can see the microstructure with its very fine grains that are so important for the performance of zirconia. As an example for the implants that we were able to manufacture, or our customers were able to manufacture with zirconia, here is the suprasternal jar implant that was a great success in it healing in very well, and the soft tissue formed perfectly over the implant. There are articles and interviews with our CEO online available if you are interested in this. Because I showed before the skull implant, and great example for the advantage of ceramic in implants is that they are, for example, are not heat conductive, and they are usually very well accepted by the body. Another implant example for zirconia, and a very good example on what is one of the main advantages of LCM are the dental implants. So here the most important thing is precision and reliability. You can print these implants from zirconia, ATZ, and silicon nitride, but the most important thing in all of them is you have a high design freedom, and there is no post-machining necessary. You can also produce a very high quantity of it with a tailored surface. The advantage of LCM is that you build all of these parts on the building platform as once. You light every layer, every part at the same time, so it doesn't matter if you produce one part or if you produce 50. Here is a close-up because the last picture does not give the screw nut justice. You are able to perform to print and generate inner working frets, which is basically impossible to manufacture in other technologies. Now we move over to the calcium phosphates. These are our so our implant materials that are resorbable and biocompatible and osteoconductive and inductive. As you can see on the right-hand side, there are already in use by customers for certain applications in implants, and I'm always impressed by this figure, by seeing what our technology can contribute to the implants. Therefore, for example, I have two examples here. This is hydroxyapatite. One is the skull implant, which of course, being able to generate patient-specific designs with a porosity that you as a customer can choose is a huge advantage. The surgery is faster because the fit is already better, and you don't need to remove parts from other parts from the body to replace existing bone, which makes it much better. Another one would be the critical bone defect in the arm bone. This is what is important here is that you can generate the correct angle of the implant to match the defect in the bone. This is a huge advantage, and it also delivers an excellent osteoconduction. The next one I want to show is Lithocon ATZ980. So this is an ATZ, an alumina toughened zirconia with a ratio of 80:20 between zircon oxide and aluminum oxide. This is also a material great for medical implants, but also for technical applications. It's very good processable. The processability is very good, and the mechanical properties, if processed correctly, are outstanding. An example for ATZ would be the ceramic ear molds for hearing aids. Here you can see a part that is under 1 millimeter in wall thickness overall, but the dimensional tolerances are less than 50 micrometer, which for a free form is very impressive. The inner channels are optimal for sound transmission, and you can produce 15 ear molds per building platform on an S65. Another example would be the cutting tools printed from ATZ. So here you have the advantage that it's an all ceramic part, so you will not generate metal debris in, let's say, when you drill a bone. You can realize complex designs as to your liking. We, for example, had a feasibility study with customers where they tried out over 30 designs at once on one building platform and were able to test it afterwards, which is of course another huge advantage of having an additive manufacturing technology. A more technical material would be the aluminum nitride, our Lithoflux. With here the main ceramic characteristic, of course, is thermal conductivity. So we reached 212 watt per meter and Kelvin. For cooling applications, the design freedom is incredible, and I am convinced that this will be a very important materials in the next years when the people realize what they can actually do with our technology. It goes without saying that the quality of the ceramic is for us the most important part of developing slurries, since if you want to reach good thermal conductivity in a ceramic, the ceramic needs to be perfect. The last material that I have for you today is silicon nitride. It's also a non-oxide ceramic. It's a mixture of alpha and beta silicon nitride, and our silicon nitride, as most silicon nitrides, is Cylon, which means it uses sintering aids of aluminum oxide and yttria oxide. Silicon nitride has a few very outstanding properties, even in the ceramic world. For example, the excellent thermoshock resistance, while also having a low thermal expansion. You can work this material at high temperatures as you could on room temperature. I chose silicon nitride to show off how we compare ourselves. If we develop a material, we aim to achieve the same properties as the powder supplier would traditional forming get. And here we have, for example, density, the hardness, BXL bending strength, and the thermal conductivity reached and shown that we are on par with traditional manufacturing. On the right hand side, you see the microstructure of silicon nitride. As you can see, there are no defects or anything. And lastly, an outlook for a possible silicon nitride application would be implants for humans, like for the skull implants, because with silicon nitride you have the advantage that it is translucent to X-rays, CT scans, and MRIs. And as Gerardo already said, it has very outstanding properties for reducing the risk of infections. That's everything from my side. I also want to point out that we are having the AM Ceramics in Frankfurt this year, and of course we would like to meet you there.
Dear participants, we are waiting for your questions. Yeah, first question is from defense industry. Thomas, to you. Which of your materials is the most resistant to thermal shocks?
Thank you for the question. For thermal shock application, I for sure would go for silicon nitride or for silicon carbide.
Silicon carbide,
that
right?
is, yeah. Mm-hmm. Silicon carbide, of course, is very challenging to process. So if the application is doable with silicon nitride, then I would go with that. But if the customer has experience with silicon carbide, we can also work together on that front.
Mm-hmm. The other question about the post-sintering. Could you provide information regarding post-print sintering?
Do I understand correctly? Post-processing after sintering?
Yeah.
Yeah, of course, we try to manufacture as close as possible to the final shape, since post-processing of ceramic is always a very expensive endeavor, and it's actually one of our main advantage to be able to form stuff like a thread or like the geometry is very near to the shape that they are used. So most of our applications have no post-processing.
Mm-hmm. Thank you. And the other question from the defense industry again. In what types of applications do your defense industry customers use Lithoz?
A very understandable question, but this is one I cannot answer.
I wanted also to add a little bit that probably in the defense industry, most applications are not are confidential, so it's not possible to disclose this information in this area.
Okay. And the other one, which materials that are difficult to produce with CNC can you manufacture precisely directly?
If I understand correctly, is the question which materials we can process. So basically, as I mentioned at the very beginning, we are a manufacturer of the printers and the slurries, so the printer and the material. So in theory, we can process any powder that is available in the market. As in the slide that Thomas also mentioned, so we have dielectric ceramics, we have piezo ceramics and stuff like that. So in principle, there are no limits of which ceramics we can process in theory.
Thank you. A question from the academia, as I remember. How is the biocompatibility of silicon nitride? Does this have a long degree thermal degradation as zirconia?
No, the degradation of zirconia is a solved problem and comes from the stabilization via the yttria content. And since silicon nitride is not stabilized via ITER or geometry stabilized, it should not thermal degrade. But it's well documented in literature, I think. So I even linked the paper in the presentation in a QR code. So that should be fine.
And again, could you explain the differences in applications of hydroxyapatite and tricalcium phosphate materials in the medical field?
Yes, that's also a good question. It comes mostly down to customer preference. So some customers prefer to work with TCP, with tricalcium phosphate, sorry, and some prefer to work with hydroxyapatite. It's always like what the customers knows better. In theory, the resorption of TCP is faster than the resorption of HA. So HA is considered a permanent implant for some, let's say, for some regions, and TCP is a resorptible material that is currently getting more focus on.
Mm-hmm. And the other question about the accuracy. Could you provide information regarding dimensional accuracy after the sintering?
Yes. This is actually one of our strong suits. So I think the best optimized application I have in mind is the brackets application, where we go down to a few microns, I think 5 to 7. After sintering, yes. And also the reproducibility is a strong suit of our technology. So once we have the geometry accuracy, we are able to reproduce it. This is always a process. So you cannot, as all technology, you cannot expect it to have this without putting work in. So we have a very capable application teams that develop the applications together with our customers. And this yields then the best results.
Okay, can you please explain the average roughness for the surface quality?
This is, of course, depending on a lot of parameters. So I can give you the feedback that some customers already thought we are too smooth, since we can print between 10 and 100 micrometer. And if you print in 20 or 25 micrometer, and then it shrinks by 30%, there is not much left to give you any roughness. So, and also with the new software, with the digital surface enhancement, you can even print a circle on a pixel-based grid. So there is very low surface roughness.
The other question from the medical industry. How long does it take for patient to heal with the calcium phosphate implants? Like, how long does it take to body to remove from itself?
That's a very fair question, but I am not capable to give a concrete answer. But I can point you to academia. So a customer of ours published a few papers on this topic recently, and I would go with that. So I am not completely qualified to say that. There is, of course, it's a range. You have to have to into account that how old is the customer, how big is the defect, what porosity did the people use. So there are so many factors, but it's all available on open source papers. So
okay, thank you.
Basically, if there is on our website, we have a link to our papers. So probably that would be the first source of information to go to our website, to these resources area. I understand we have this very well linked to all the papers that are available.
Okay, that's all is done. Is there any question? Yeah, there is no question here. Yeah, I'd like to thank all participants, and once again, you, Gerardo, and Thomas. Thank you for joining the webinar. See you in our next session.
And also thank you to infoTRON for organizing this webinar. Thank you very much.
Thank you.
thank you.